The seemingly straightforward act of reversing a common device can often unveil surprising complexities in the underlying physical principles. The Feynman sprinkler, a thought experiment popularized by the insightful physicist Richard Feynman, perfectly exemplifies this phenomenon. By considering a submerged S-shaped sprinkler that intakes rather than expels fluid, Feynman posed a deceptively simple question. In which direction, if at all, would this reversed apparatus rotate? This query delves into the heart of conservation of momentum within fluid dynamics, revealing a nuanced reality that challenges initial intuition and underscores the importance of rigorous analysis and experimentation. The initial, and perhaps most intuitive, response to the Feynman sprinkler problem is that it would rotate in the opposite direction to its conventional counterpart. After all, if expelling water generates a reactive force causing rotation in one direction, wouldn't the inverse action produce the opposite effect? This line of reasoning, however, overlooks the fundamental differences in how momentum is transferred in the two scenarios. In a standard sprinkler, the expelled jets of water carry momentum away from the device, and to conserve angular momentum, the sprinkler itself must rotate in the opposite sense. This is a direct application of Newton's third law. For every action, there is an equal and opposite reaction. However, the situation becomes considerably more intricate when the flow is reversed. In an idealized scenario involving a non-viscous fluid, the water would be drawn radially inward from all directions towards the sprinkler's nozzles. Unlike the focused jets of an expelling sprinkler, there are no concentrated streams carrying a net angular momentum towards the device. Each infinitesimal element of the incoming fluid possesses a velocity component directed towards the center, but these components, when considered collectively, cancel each other out in terms of generating a resultant torque on the sprinkler. Consequently, in this theoretical realm of an ideal fluid, the Feynman sprinkler should remain stationary, defying the initial expectation of reverse rotation. Yet, the idealized world of frictionless fluids often diverges from the tangible reality of experiments. Real fluids possess viscosity, and experimental setups inevitably introduce frictional forces. It was with the advent of highly precise experiments, employing ultra-low friction bearings, that the true behavior of the Feynman sprinkler began to be unveiled. These meticulous investigations revealed a subtle yet significant phenomenon. The reverse sprinkler does indeed rotate, albeit very slowly, and in the opposite direction to a conventional sprinkler. The explanation for this unexpected rotation lies in the intricate dynamics of the fluid flow within the curved arms of the sprinkler. Even though the inflow from the external environment appears radially symmetric, the constrained geometry of the sprinkler's internal channels leads to the formation of internal jets as the water is forced to navigate the curves. Furthermore, as the fluid traverses these curved pathways, centrifugal forces come into play, creating slight asymmetries in pressure and flow distribution within the arms. These subtle imbalances generate a small net torque on the sprinkler. Additionally,